Okay, for cyclobutadiene, its MO, let's talk through what this looks like. This is C4H4, and so when we have a larger molecule, we're not going to worry about putting things on the left or the right, but just qualitatively what this is going to look like with all the AOs that are going to go into that. In this case, since we have 4 carbon atoms, each of those is going to contribute a 2s and 2p, right? There's 3 of these 2p orbitals in that subshell. So 4 orbitals each, and each hydrogen will contribute its 1s. The relative energies there we can get from the handout. Okay, so using the information here, the 2s orbital in carbon is at negative 19.3, so we have the carbon 2s, there's 4 of those. We have the carbon 2p, that's at negative 10.7, and the hydrogen slits right in the middle there. So we've got 4 hydrogen orbitals here. These are the hydrogen 1s, and then slightly higher than this are the, again, I'm not going to put them all on there, but all of the carbon 2p orbitals start in there. If we count them all up, we have 20 atomic orbitals, 4 each for 4 carbon atoms, plus 4 on the 4 on each of the hydrogen atoms. Then when we think about making the molecular orbital theory, we have to think about symmetry elements. There's a lot of symmetry in cyclobutadiene. One key symmetry is the plane of the molecule. So this is a reflection plane right in the plane of the molecule. I'll use that as my first symmetry element. Then a couple other ones are this plane here going right through vertically here, and then the other plane here like this. If I just draw this top down one more time, I've got this plane, and then the plane of the molecule. I'll do the plane of the molecule first. Again, I'll call that the XY plane, or sorry, the YZ plane. Yeah, here I'm going to call it the XY plane. Then the Z-axis is going to be the vertical axis here, so I'll call this plane right here the XZ plane, and this the YZ plane. So my axes here, X, Y, and then Z is coming into and out of the page. Importantly, when we look at the symmetries here, at this point when we have bigger molecules, we need to combine atomic orbitals to form symmetry adapted molecular orbitals that have the proper symmetry. So to take an example of that, those hydrogen 2s orbitals on their own don't respect the symmetry elements. So here are the hydrogen orbitals out here. There are 4 of them, one out here, another one out here, another one out here, another one out here. When we form the molecular orbitals, the first thing we do here is form symmetry adapted molecular orbitals. So these are called SALCs. These, again, respect the symmetry of the problem. So for the hydrogen 2s, we can form orbitals that look like this. We can form the all-in-phase combination, something that looks like this. We can form a combination that looks like this, all out of phase. Both of these orbitals respect the symmetry. This one is SSS. This one here is symmetric in the plane of the paper, but it's anti-symmetric with respect to these 2 planes. So this one would be SAA. And there's going to be 2 more combinations here. It turns out that in this case, because of these 3 symmetry elements, I'm going to use these 2 as my combinations. I'm going to look at one that is these 2. Actually, I'll do this one here. Do this one. Okay, so these other 2 orbitals here, this one up here, this is going to be, again, I'm using, what is my order here? I'm doing this one first, then I'll do the XZ axis second, and then the YZ axis third. So this one is, this one would be, according to that, SAS, and this one would be SSA for this last orbital. With those symmetry elements out of the way, these are probably still the same energy, basically, as the original orbitals. Important to note because there's no real overlap between these orbitals because they're so far away in place. So even though we formed these SALCs, they're still basically at the same energy. So we've got like SSS X2, we've got an SAS and an SA. Once we've formed these symmetry-adapted linear combinations of atomic orbitals, then we can go in to make the MO diagram. I'm not going to do that for all of these right now. We'll see in a second sort of why. But important to note that all of these orbitals are symmetric with respect to the plane of the molecule. And so these are all going to be sort of sigma type orbitals because of this plane. So again, because there's that symmetry element, we can make this clean separation into sigma and pi bonding orbitals. When we go through and make this diagram, the rough answer we expect to get, if you think back to organic chemistry, we've got all of these carbon 2p's, we've got these hydrogen 1s, and the carbon 2s. Largely what we're going to expect to get here is we're going to get sigma bonding orbitals down here. There's going to be a bunch of sigma bonding orbitals. We're going to have pi bonding orbitals here, pi antibonding orbitals up here, and sigma antibonding orbitals up here. That's sort of what we expect to see in our MO diagram. Because of the different symmetries, the sigma framework, which is symmetric with respect to this plane of the paper, and the pi framework, which is anti-symmetric with respect to the plane, right? Each of these p orbitals that I have is going to be anti-symmetric here. It's got a positive lobe up here and a negative lobe down there, so these are all going to be anti-symmetric there. So I can make that clean separation into a sigma framework that describes all my sort of sigma bonds that are symmetric with respect to the plane of the paper, and the anti-symmetric ones. Okay. With that out of the way, now we're just going to focus on the pi framework. None of the hydrogen atoms contribute to the pi framework, and none of the carbon 2s orbitals contribute to the pi framework because they're all symmetric. The only orbital that's going to be anti-symmetric with respect to the plane of the paper and contribute to the pi framework is the single 2pz orbital on each of these 4 carbon atoms. So I'll simplify things by just looking at the pi framework. I'm just going to have 4 atomic orbitals that contribute. It's these 4, the 2pz on each carbon. And in this case, luckily, our symmetry-adapted atomic orbitals that we made up here are actually going to be pretty much what the pi orbitals look like, except this is from sort of a top-down view. So I'll sort of show what these symmetry-adapted linear combinations look like. They look exactly like this. I'll show them in this top-down view. So let's do our salx here. Our salx are going to be this one, this one, this one, and this one. And just to be clear here, I'm representing, right, so this is, again, there's only one symmetry element here. Well, there's the 2. They're all anti-symmetric with respect to the plane of the paper, but there's these 2 symmetry elements. Again, my order here, these are all anti-symmetric because they're pi orbitals. Then the other 2 symmetry elements doing, what did we say? We did this XZ axis first, so this is ASS. This one is anti, and then anti, so this is anti with respect to all 3. This one right here is, again, symmetric with respect to this first element, and then anti with respect to the second. This one over here is anti, anti, and then symmetric. So we have the different symmetry-adapted linear combinations. Now we can actually go through and determine their energies. So the energies that we're going to get out of these come right here. The lowest energy orbital is going to be this one. A good way to understand that, and again, this is shorthand for, again, if I drew the full thing out, I would have that same, but opposite on the below the plane. So we just view, this is this sort of top-down view, staring right down the p orbital. Again, that just makes it a lot easier to draw and look at. So this is sort of what that orbital actually looks like. I'm just sort of looking at it from directly the top because that makes it a lot easier to look at. Again, this one, if we want to figure out its energy, it has 4. This is the equation from the handout. We look at bonding contacts minus anti-bonding contacts over the number of orbitals. Now, in this case, what can we do with these? Well, in this case, we have a, let's take a look. In this case, we have 4 bonding contacts between nearest neighbors. 1, 2, 3, 4. There's no anti-bonding contacts because these all have the exact same phase. And there's 4 atomic orbitals. So this is 4 minus 0 over 4 is equal to 1. This is basically a fully bonding orbital. Each orbital, is interacting in the most beneficial possible way, making bonding overlap with its neighbors. So this is going to be a very low energy orbital. On the other hand, up here, we've got this orbital. If we look at these contacts, again, looking at the contacts between each pair of atoms, this is an antibonding contact, an antibonding contact, an antibonding contact, and an antibonding contact. So this is 0 minus 4 over 4 is negative 1. This is the most antibonding possible orbital that I can make. Now, what about these other 2 orbitals in the middle there? The 2 in the middle. Let's take a look at, say, this orbital right here. Okay, if we look at it, this orbital has, counting our contacts, an antibonding contact here, a bonding contact here, an antibonding contact here, and a bonding contact. Okay, when we look at the overall energy then, 2 bonding contacts minus 2 antibonding contacts is 0, or a net non-bonding orbital. The same holds true for the other orbital that looks like this. The AS orbital is also non-bonding, 2 bonding contacts and 2 antibonding contacts. That's going to be true anytime we have a greater than 2-fold symmetry axis in our molecule. So in this case, we have a C4 or 4-fold rotation axis. If we rotate the molecule 90 degrees, it comes back the exact same. And that is going to lead to the degeneracy in the molecular orbital diagram. Again, something we'll see in the higher levels of theory as well. When we fill in the electrons in our diagram, we have 2 electrons in this bonding orbital and then 2 electrons, 1 spin up in each of these non-bonding orbitals because we have those 4 pi electrons in the molecule. Because there's 2 unpaired electrons, that's an overall triplet. And again, because we are only getting 2 of those electrons into a bonding orbital and the other 2 are in a non-bonding orbital, it's on net a very unstable molecule. Most of the time, for most molecules, what this picture is going to look like is you have your electrons coming in, and normally we're going to be able to get a couple of bonding orbitals out in the diagram, and then we'll have a couple of anti-bonding orbitals up here. In this case, this is really unfortunate that we have these 2 non-bonding orbitals, so these 2 electrons, whereas normally they would get lower in energy, here they didn't decrease in energy at all. This is related to that 4n plus 2 rule in organic chemistry about aromatic and anti-aromatic systems. This we would call anti-aromatic because it's got, sort of is less stable than you would predict from just looking at the Lewis structure. Yeah, again, this is something you could do on your project if you want, and for the homework ones where you're doing things like this, counting the contacts is useful, and I would recommend then just using, just like we did in class, that PM3 theory, view the orbitals. Again, nice connection between this Huckel and semi-empirical theories and the qualitative MO that you've done previously.